Professor Anton KOKALJ will give the hands-on session about SCF calculations and post-processing. Before starting, let me just say a few things regarding the organization. So basically, from yesterday, we saw that Slack is very effective for the hands-on session. So please, all the participants, please write all your questions on the Slack channel. And the tutors, please check the Slack channel for questions, because in that way, there are more people who can monitor the questions. So there are more chances that you get an answer. And yes, so use the Slack channel, because we also have threads. And here, if you write here on Zoom, the chat will scroll down and we lose the questions. Another thing, please remember to answer using reply in threads. So the answer will stay bound to the question, and it is easy even to understand the flow of the conversation. So for both participants and tutors and whoever, reply in thread whenever possible. And use the main chat only to open a new thread, so for a new question. Another thing, one last thing, we have the breakout rooms. As you see, there are 4 rooms, one per tutor. So we have 4 official tutors for this session. For the tutors, if you read the questions on Slack and you feel that you can give close assistance to people who are asking questions on Slack, feel free to write on Slack, join to my breakout room. So when the participant reads this sentence, you can find here on Zoom the breakout room menu in the bottom bar, and you just join the breakout room of the tutor who answered you on Slack. So I say it again, just for clarity, participants ask questions on Slack. If the question is tricky or participant need closer assistance from the tutors, the tutor will read the question and answer, please join to my breakout room. So the participant can join the breakout room from the bottom bar here. You see that the breakout rooms are named after the tutors. So Malika tutor room, Podberznik tutor room, Sapati tutor room. So if one of those tutors answered you, join my breakout room, you come back here on Zoom and enter that breakout room, where of course also the tutor will join the breakout room, and you can chat there and solve whatever issue. So let's try this way, which seems to us to be the most effective so far. Sorry for these words. Now
just a very short recommendation. This is Stefano Baroni speaking. Concerning the usage of breakout rooms, I would recommend all the tutors to use them as much as possible, particularly for technical questions, technical and seemingly trivial questions, such as the location of buttons on the screen, the simple setup stuff that is trivial to explain in words and may take several lines and trial and errors to explain on the chat. So feel free, please, to use at your discretion, of course, but the chat rooms as much as possible. Also, I've seen that that some questions get multiple answers, which is good, of course, but there's kinds of penalizes the optimal allocation of the tutor's time. Here again, if some of the questions can be discussed in breakout rooms, this would probably save some of the tutor's time. Thank you very much, and have a profitable morning or afternoon, whatever it is at your place, night.
Thank you very much, Stefan. So please, Tone, let's begin the hands-on.
Okay, so thank you very much, Ivan, and thank you very much to Stefano for all the explanations. Now let me try to share the screen first. Okay, so can you see my screen?
Yes, yes, we can see it.
Yes.
Okay, fine. Okay, so hello everybody. My name is Anton KOKALJ, known as Tone to colleagues and friends. I come from Jožef Stefan Institute from Ljubljana, Slovenia. And the subject of today's hands-on session are convergence tests. Yesterday, after the excellent presentation given by Ralph Gebauer, there are a lot of questions on the Slack. How do I choose a proper set of key points? How do I choose the proper cutoff energy? And so on. And so so there is no general answer to such questions, because first, the answer depends on the system and the answer depends on the context. And during today's hands-on session, you will learn how to try to give an answer to such question for a given, let's say, particular system. Okay, so here is the scheme of today's hands-on session. So first, we will make some basic convergence tests for silicon bulk. This is located, I will show later, in the directory example 1, silicon. So here we will test cutoff energy, we will test K points, and so on. Then we will do one metallic system, aluminum in particular, and here we will see this smearing issue that Paolo described this morning. And then we will go to example 3, which is iron. And for iron, which has a 3D states, we will use ultrasoft pseudopotential, and it is also magnetic. And so we will see this kind of how we need to increase the cutoff energy for the charge density beyond 4 times that of the wave function. So there is a lot of examples here. So I'm not sure we will be able to do all. I will be able to cover all in 2 hours, but nevertheless, these slides contain all the information. And so now it depends. You can follow me when I will do the examples, or you can just listen to me and then you do these examples later on. It depends on each particular participant, what she or he thinks is the best for her or him. Okay, now this is something, now comes the point where we will do this more or less every day. We will update, let's say, these exercises. And to do that, I will show later how to do. Git pull should be sufficient, but if you have changed some files yesterday, then git pull may fail. And if this is so, then here at the bottom of the page, you have the 3 commands that you need to do, and then your exercises will be updated. Okay, and now I will shift from these slides. And I maybe just one useful information for those of you who are not used to Linux. So do you see my mouse pointer? This is a question which is important, I think. Can you see my mouse pointer?
Yes, we do. Yes, we do.
Okay. So you see here at the bottom, you have these virtual workspaces. And this sometimes is very useful for organizing if you have multiple open windows. Okay, so now this was already described in Friday and yesterday. Here we have these exercises organized in per day basis. So today is day 2, and so we can double click this, day 2, and the file browser will open. And now for each, let's say for each day and for each exercises, we have 2 different sources of information. The first one, which is in the top directory of a particular day, there are hands-on slides. So these are the slides I just showed you before the first 2 pages. But then there is another source of information, which is a README file. And this README file exists in every directory. So I now jump it into example 1, and you see README file here. So the information contained in this hands-on slide and the README slide is a bit complementary. So these PDF, these slides, they contain, let's say, a more descriptive, more explanatory description of the hands-on exercises, whereas these README files are more like cooking recipes. It goes like, okay, let me open it. So if you double-click it, it will open in a Firefox browser. And so this README file is more like a cooking recipe. It says, okay, in this exercise, you need to do a calculation A like that, and a calculation B like that, and a calculation C like that. So these are these 2 information that you have in order to understand what each particular exercise is about. Now let us do this first thing of the day. So we can right-click on the file browser. Here I have open terminal, and then I will do git pull. So this is the first thing to do. And if git pull fails for you, for me, I am already up to date because I've done this before. You can do git stash, git pull, git stash apply, and this is described on the second page of the slides. Okay. Now let me go back to slides. And the first example is silicon. And here you will see some explanation of the structure of the input file. So you can read this by yourself. Instead, I will go to example 1 like that. And of course, if you don't know or if you are behind me, then always you can look at the README file and there is the explanation what to do. And so now I am in example 1, but maybe before proceeding, just a question. Are these fonts in this window large enough or should I enlarge them? Any feedback?
Maybe you can enlarge a little bit.
Enlarge a little bit. Okay, let me try if that will work. Okay, now it is a bit larger. Okay. And so here inside, again, in this example, silicon, I have several sub-examples, a README file, and here is the input file for the PWX. And we can open it, for example, in Emacs, or another way is to use a file browser. And so here we can see some name lists, and in these Emacs modes, everything that is red means comment. And also this hash here, this means comment for the cards, but is not colored red in Emacs modes. Okay, so this is the basic structure of the pw.x input file. And if you are just interested in the name, so what is PW SCI, SCF means, you can go here to Firefox. Now, because the Zoom is running, it is a bit slower. And then you can go to this how to, and you have here the file name conventions, and you can read the logic of how the files are made. Okay, fine. And so suppose that you don't know what a given variable is. So we have prepared for you, this Firefox with the buttons. And here, if you click PWX, then of course, for each particular variable, you have the explanation. For example, if I go to the calculation, I can see different types of calculations that can be done in the PWX. Now, of course, in a virtual machine, all this is arranged for you, but maybe later on when you will not use the virtual machine anymore, suppose that you want this information. So how we can do this? Well, we Google it, and let's say that I'm interested in the NEP description. So in the Google, I would say input nep.html. And so the Google is smart, and the first hit is the description about the NEP program. Otherwise, this information is also contained on the Quantum Espresso webpage. So why I did this NEP example is because here you see a lot of buttons, but because there are so many of them, we did not notice that NEP is missing. NEP will be used next day, and so we can just add a NEP button. So this can be done very simple. I just drag this somewhere here, but I've done this yesterday for myself, and then maybe I can just make a shorter description like that. Now I have two NEP buttons because I've done yesterday this. So I will remove this one. Okay, this is just, if you would like to know what a given variable is, go to, today we will use PW, we will use PP, we will use bands, we will use DOS, and so on and so on. You go here and then you find the information. Now it is time to go on, and I go back to slides. And so one of the first thing one of the important thing when we try to model a given system is to input the structure. And so silicon is crystallizes in a diamond structure. And so now, how do I visualize? So here I have this input file, or even here, of silicon. So it is EBRAV equal 2. So if you will go to this PWX description of the input file, you will click EBRAV. You will notice that EBRAV equal 2 means FCC lattice. Okay, and in order to visualize this structure, and then you can see we have two atoms in the unit cell, and this is NAT, means number of atoms, and number of type of atoms is just silicon and two atoms. Okay, and I can visualize it like that: XCRISDEN minus minus PWI, the name of the input file, and so this is the reduction. So if I have a crystal is a 3D system, I do not reduce. If I have a surface, I can reduce to 2 dimension. If I have a molecule, I can reduce to 0 dimension. Now we have silicon bulk, so no reduction of the dimensionality. And now this is a silicon structure. I can even display atomic symbols. And now I don't see any bonds. And this is sometimes annoying. I just show how you can display bonds. You go here to atomic radius, and you enlarge the chemical connectivity factor. And you press update, and now I have the bonds. Okay. But now, and very important buttons are here on the bottom. This is kind of nicely tessellated unit cell. This would be just a translational asymmetric unit, But now is a problem. Here we can see that there are 8 atoms. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. But here in this input, I just specified 2 atoms. So how is this possible? It is because we are looking at the conventional cell. If I want, and the code is smart. And because the conventional cell is 4 times smaller, now I have just 2 atoms, and this is basically what code calculates. This is why we just specify here 2 atoms. Okay, and now to really verify, that this silicon structure is composed of 2 FCC lattices, let us play a bit. So I will say number of atoms 1, and then I will comment one of the silicon atom, and then I modify the input file. Now I will press reload, and I obtain something like this. And here you can really see that this is the FCC structure. So silicon, basically we have 2 units, 2 atoms per unit cell, and so basically we have 2 FCC lattices displayed, one with respect to the other. So now I will undo these changes. Okay. So this was a bit of explanation how we visualize the structure, how the FCC structure of this conventional, this interplay between conventional and primitive structure. But now it's time that we do the first convergence test. Now let me go back to slides. Okay, so basically what is here, I now did a kind of a real demo. Oops. Okay, and then here is also some explanation of the key points. And okay, but maybe we can just do the first calculation before we do the convergency tests. And yesterday on the Slack, there was some confusion about this usage. This flag means minus input. It can be minus I, minus in, minus imp, whatever. Instead of that, we can also use this, what is this, smaller than redirection operator, but we cannot use both, just this or that. But notice that this is not recommended on parallel machines because it cannot work. So this minus in is more secure, and because it always works in a sense. So I can copy maybe this. Let me see. And I do a simple SCF calculation. And this will be super fast because even with one processor, because this is really a very simple system. So you see less than 1 second. Now, okay, this was a simple calculation. And in this virtual machine, so if we would look here, we have this out dir and pseudo dir commented, and there was some discussion yesterday on the Slack. And the reason is that we are using in virtual machine this ESPRESSO pseudo and ESPRESSO TMP dir environmental variables. So most of the exercises for today will not explicitly set out dir and pseudo dir variables. And then, of course, you can also do something like that to see in the temporary directory. It didn't copy well. Okay. But now you can see this is the temporary. These are not quantum espresso files, but here these are quantum espresso, let's say, scratch files that quantum espresso has written in the directory. Now you see doing a single SCF calculation is very easy. And then we can also grab the total energy from the output file. We can read the output file directly. For example, if I want to, so I can create the output file. Oops. Like that. And then I can read it. But of course, I can, instead of that, also grab for, let's say, for the total energy or something like that. And this is described here on this page. But now let us go to convergence tests. And so the logic of this first exercise is the following. Let us do the convergence tests with respect to basis set. That is with respect to kinetic energy cutoff. This is the variable E cut wave function. Then let us do the convergence test with respect to K points. This is card K points. And then with the converged cutoff energy and K points, let us calculate the lattice parameter of silicon bulk. And then the bonus would be that once we determined these, let's say, converged parameters, we can calculate the band structure of silicon. Now, how one typical does convergence tests? That means if I want to do a convergence test with the cutoff energy, I need to pick a given cutoff energy, let's say 16 Rydberg, do a calculation, and then collect the total energy. Then change input file, set cutoff to 20 Rydbergs, and repeat the process, collect the total energy, and so on and so forth. And so this is very tedious to do manually, and so nobody does this manually. And so for this reason, we use scripts, which will automate the process. And what concerns the scripts, I would say traditionally, Unix shell scripts were used to this end. And here is I only hope that these characters, they are very tiny. They can be seen via the Zoom. If you cannot see those characters here, which are tiny, then, okay, look to slides yourself and you will be able to see. So this is one such Unix shell script. So it's a loop over the cutoff, different cutoff values, 12, 16, 20, 24, 28, 32. And then here you see this E cut wave function equal $E cut. And so we do a calculation and then we collect the energy in a file. So I remember when I was young, when I started to do calculations, this syntax of shell script was quite awkward for me. So I did not understood at the beginning what this is. There is another possibility, and that is the Pwtk scripts, and they are cleaner in a sense, and they are shorter. And today we will mainly use Pwtk scripts. And so the logic of this Pwtk script is the following. Here we have this load from Pwi, which means load from Pw input. We load the input file. Okay, here we then open some file where the results will be written. We do a loop over the cutoff values, and then we just set this cutoff variable and we run the calculation. Then we grab with this command the total energy, and that's it. And so I think this is in a sense much shorter and much cleaner than the shell scripts. And today we will use these Pwtk scripts. Now, if I go, so I can go to example 1, E cut. If I go here inside, I go first to the classic. If I go here inside, I see this E cut wave function script that you saw before. I will just use different color in order for the script to be, no, just the other way around, to be better seen on the screen. So this is the shell script I've shown before. Now maybe with a bit larger characters, and this would be then the Pwtk script. So if I do ls, I can see this Pwtk script. So is a bit longer than before because here we have some comments. These are comments, and due to that it is a bit longer. And here we have this sec command. So for those of you who do not know what sec is, this is also a Unix command which gives you a sequence of numbers, something like that. And so this sec will just go 12, 16, 20, and so on. Okay, and so you see a loop over E cut values. We set the E cut wave function variable, and then this run Pw is a command how to run the Pw executable in Pwtk script. And now I will execute that. And this is, so the calculation is running. It is quite fast. Okay, and so this is my result. And so now we have, let's say, the first answer. So what would be the sufficient cutoff? Suppose, let's say that there should be, let's say, the total energy converges slowly. Maybe other properties sometimes can converge faster. But let's say as a rule that I should be converged between milli-Rydberg or so per atom. Here I have 2 atoms, which means that more or less, let's say from 25 Rydbergs on is more or less okay. So you can see it. Very low cutoff. First, it changes very rapidly the energy, and then it saturates and it converges. So, and now I can remember this value because later on I will use this value, this cutoff value to calculate the lattice parameter. So maybe something like the 25 or 30 Rydberg should be more than sufficient. Maybe just because I've shown you this Pwtk script, I go here. And so here is a basic explanation of the logic behind these Pwtk scripts. So I'm sorry because maybe we are really confusing you, because those of you who are new to Quantum Espresso, they are struggling with the input syntax. and now we are adding on something on top of it, but I think there is no rescue from that, because if we want to do a convergency test, we need to run a lot of calculations, and scripting basically is the only reasonable possibility to do. So here you can see this would be a quantum espresso input on the left, and on Pwtk script, the input is specified very similar. The difference are here we have these curly braces, and then in PW in the terminal is run like that. In Pwtk script, we run pw.x calculation like with run pw command, and from the terminal, the script is executed like Pwtk and the name of the Pwtk script. Of course, then here on, you can read more information about the Pwtk scripting. And then at the end, you also have the website. Here we have the explanation of the commands that we will use today. Load from PWI, which is load inputs data from the existing PW input file. Then this PWO.ene returns the converged total energy from the output, and so on and so forth. And then if we go to a Firefox, you also have this button here, and here you will see the information of the Pwtk. And maybe if you are interested, if you want to learn, here is a way to go. You click this documentation, and then you follow these instructions here. Okay. Now, so we've done the first test. So we see that some 25 or 30 Rydberg is more than enough for this case. And now let us go to a second example. So I can go one directory back, and we see that the second example is K-points. Of course, then in each directory you have these README files, so you can read what should be done with this exercise, but I think it's pretty obvious. We have this K-points script inside. So let me open it. And so what we have here, we load input from some existing file, which is one directory back, and then we will scan over the K-points 2, 4, 6, 8. This 2, 4, 6, 8 basically means you can see here. So K-points automatic, and this automatic is what Paolo described this morning, that there is this automatic feature which constructs the K-point mesh for you, and then the code just uses the K-points in the irreducible wedge of the Brillouin zone, and of course the code knows how to calculate the width of a particular key point. And so basically this K2 means 2 by 2 by 2 K-mesh, and we use shifted K-mesh. So this means 1, 1, 1. And okay, and then we collect the total energy, and at the end we plot the result with the blue plot. So let us run this script. So now you see 2, 4, 6, 8, and now I have the result. And so what does this result tell me? You can see how the total energy behaves. So here is the total energy for the 2 by 2 by 2 mesh. And then you can see that from 4 by 4 by 4 on, the total energy is more or less converged. So the answer for the silicon bulk is 4 by 4 by 4 K-mesh is enough. And now we know that something like, I don't know, 25 Rydbergs and 4 by 4 key mesh is okay for silicon bulk. With doing that, with finishing the first two examples, we can go to example 3, and this has some, let's say, maybe not so clear name, ALAT. ALAT stands for a lattice parameter. And so now you know what ALAT stands for, and so the purpose of this exercise will be to determine the lattice parameter of silicon bulk. Now, so here we have the script which is prepared. So let us open it and let us read it. So again, the logic is the same. We load the input from this pre-existing input file, but now let us read the comments. Here it says, please uncomment and insert value as determined in the ECAT wave function exercise. So I will uncomment this, and let me say, okay, silicon is a super fast example. Maybe I can take 30 readings, or even maybe 25 would be more than enough. Please uncomment and insert values as determined in the K points exercises. And we just saw that for the silicon bulk 4 by 4 by 4 shifted mesh is more than okay. And now I am more or less ready. And so here you can see for each ALAT, so is a loop over the lattice parameters. And so we use this sequence. So we will scan from 9.7 bores to 10.7 bores with the step of 0.1 bore. And so you see that for each ALAT, we set in the system the cell DM of 1, basically, which is basically a lattice parameter in Bohr units. Then we run the calculation and we collect the result. Then we will plot the result with the GNU plot. And then at the end, we will also execute the EVX code. EV means energy versus volume. And this EV will give us, will determine the minimum of the E versus lattice parameter curve. So it will give us the lattice parameter, and it will also give us the bulk modulus. And okay, so I think is time that we run this example. So we say Pwtk ALAT, and so we go 9.7, 9.8, 9.9, 10. So let us wait a bit. We go to 10.7, 10.7. So almost done. Okay, so this is the result. This is the result. And so you can see that the lattice parameter should be around 10.2 Bohr. And now in order to get rid of this GNU plot window, either press this X, or you just press enter in the terminal. And now this is the output. This is the output of the EV command, which was run here. And so here you can read this output of the output of the EV.x command, equation of state. So the input was here. You can also run this code from the terminal. So it will ask questions and then you can answer. So we have chosen Moore-Nagana equation of state. And this would be the lattice parameter in Bohr. This would be in atomic units in Bohr radius. This would be the lattice parameter in angstroms. This is the bulk modulus. Here you can see lattice parameter and the calculated energies, the fitted energies. Here is the pressure and here is the enthalpy. And now just a homework. So if you compare the total energy and the enthalpy, you can see that if the lattice parameter is smaller than the equilibrium lattice parameter, then the total energy has a lower value than enthalpy. But if we go beyond the lattice parameter, so then you can see that total energy is has higher value than the enthalpy, and so the homework is you need to figure it out why this is so. Okay. So with doing this, I think we have completed the first exercise. So the first convergency tests. So we now know the cutoff energy. We now know the K points, we know the lattice parameter, and now we can do bonus material, which would be the band structure. Now, for the sake of time, I will skip this example. It is a nice example, but I will just tell you how you do it. So you read this README file, and this README file will instruct you to edit these bands, Pwtk script. And so here you will insert the lattice parameter. You will insert the cutoff, the wave function cutoff, and then you will insert the key points. And now here you see a remark. So the script is suggesting you to use a non-shifted mesh. And yesterday there was some discussion when we use shifted mesh and when we use non-shifted mesh. And so in general, I would say we use shifted mesh, but, or maybe I should do the example. But if we want to plot, let's say, the density of states, it is maybe better to use non-shifted K-mesh, because those critical points like gamma, X, so in the center of the Brillouin zone and of the edge of the Brillouin zone, these high symmetry K points, these are basically kind of a critical K points, and usually, let's say, the bottom of the band and the top of the band is these critical points. And if we do not, if you use shifted mesh, we will miss these points. And then suppose that you want to get an idea from the density of states plot, what is the band gap? If you do not include these critical K points, then you will get a wrong number for the band gap. So let's say for the density of states, it is maybe better to use a non-shifted mesh. If you do this example, and if you first use shifted K-mesh and then the band structure will be plotted, you will notice, and you compare the Fermi energy, you will notice that the Fermi energy extracted from the shifted K-mesh will be somewhat lower than, let's say, the eigenvalue which should be occupied at the gamma point. So you will figure this out by yourself if you will do the example. Okay. So with doing this, I think it's time we go to the second example, which is aluminum. Now let me just check the slides whether I did not forget something. So here you have all these explanations, also the plots, and maybe here I have this this band structure. Oops. This band structure plot of silicon, and you see this is a gamma point. This is K000. And if I do not include a gamma point, so if I do not use shifted, non-shifted K-mesh, I would miss this point because the mesh would be shifted. So you see this is kind for this silicon, we have the bottom of the occupied band and the top of the occupied band at the gamma point. Okay, now let us go to aluminum, which is a metal. And okay, so this would be the basic input file. We will look at it. And if you look at this in this directory at this input file, now we will notice these new variables: occupations, smearing, and the Gauss. And so this is now how to deal with these discontinuities metals, because we have a kind of occupied states, and then there is no band gap, and then at sudden from Fermi energy on, the states are not anymore occupied, and this makes problems. These make problems with the integration, and one should use a very, very dense K-mesh, or one can use a less dense K-mesh and smearing. And of course, Paolo explained this morning this business. And so the example that we will do is that we will do a kind of a convergency tests. It will be three-dimensional. So we will scan over K points over the Gauss value. This the Gauss means how much. The Gauss means how much we smear, and smearing means which type of smearing we use. So this is a three-dimensional scan, and it will take a while. And so here is a snippet of the Pwtk, how this is done. So it's a scan over the key points. Then it is a scan over different types of smearing: Gaussian smearing, Metfessel-Paxton smearing, and Marzari-Vanderbilt smearing. And then there is a scan over different Gauss values. Now let me first open. The input file. So this is the input file, and oops, okay. And these are these new variables. These are these new variables. that before we didn't have with silicon. And I think by the rest should be more or less, you should be familiar already with now. So atomic species, aluminum, atomic position. So aluminum, again, is FCC, obviously. EBRAV equal to 1 atom, but 0, 0, 0. And here are the key points, and now I go to example 1, the Gauss. And okay, here are the explanation. And this would be the script. So let us open it. So you see, okay, now it's a bit longer than on the slides because there are some comments. And okay, so you see a scan over key points, a scan over different type of smearing, a scan over different the Gauss values. And now this script takes a while because it's a 3-dimensional. And so there is quite a number of examples to run. And okay, so maybe we just wait for this to finish. It should not take more than several minutes, I suppose. And in the meantime, let me check the slides. Okay, yeah, here will be the result. And so let us, now I am at K point 12. I can read here, and K point 12 is here. So I am, but of course, each next is a slower calculation because there is the number of K points goes up as we go from 4 to 8 to 12 to 16. And maybe in the meantime, while this is running, I explained a very, let's say, one feature of Pwtk. Because usually when we scan these parameters, maybe we do not know in advance what would be the proper range of a given parameter to test. And then if this is the case, the Pwtk is smart in a sense. And so you see this comment here. What I can do is I say restart true. And then I can add I can expand the range of a given parameter. Let's say just for the sake of example, that I will expand the range of the Gauss, and I will add here 0.15 and 0.2. Now I will not yet save the file. And later on, you will see how Pwtk deals with such case where we add, where we expand let's say, a range of scanning of a given parameter. Okay, now this is the first result. This is a Gaussian smearing. And so this would be results for the 4x4 4x4x4 K-mesh. This is result for 8x8x8 K-mesh. This is result for 12x12x12. And this is 16x16x16. And so the first thing, here are several things to notice. The first thing to notice is that for metals, let's say for aluminum in particular, 4x4x4 K-mesh is not okay because you can see, you remember before for silicon 4x4x4 was already perfect. Here it is not. You can see that the total energy for 4x4x4 is sufficiently different from these more dense K-meshes. And then you can see that as we increase the smearing, these curves comes together. This is why smearing helps. So with the smearing, if we use a sufficient smearing, maybe we can use coarser K-mesh. So you can see how this difference between, let's say, 4 and the other curves goes down, and also how the difference between 8 and this very fine K-mesh goes down as we increase the smearing. But as Paolo explained this morning, this Gaussian smearing, the total energy will be affected with this smearing temperature quadratically, and basically this is what you are seeing here. Now I can, so here it says press enter in the terminal for the next plot. If I do this, now I have a Marzari-Vanderbilt smearing, and this would be the previous Gaussian result. Now you can see, because now this Marzari-Vanderbilt is what Paolo referred to as smart smearing, which was devised to, let's say, be less dependent on this smearing temperature. And in fact, you can see, at particular for this, let's say 8, 12, and 16, how flat it is with respect to the smearing. And you can also see this 4x4 K mesh. When we increase the smearing, this, let's say, difference gets smaller and smaller and smaller. So with smearing, the message would be, with smearing, I can use coarser K mesh. And now I press enter again. And here I have a Metfesdal-Paxton smearing, which is another type of this smart smearing, as Paolo referred this morning. And you can again see it is much less susceptible to the smearing than the Gaussian smearing. Okay. And now, in the meantime, I prepared the script where I will expand the range of these degauss. So I added 2 new values, and I say restart equal true. And now, okay, I need to save it. If I rerun the script, you can see that Pwtk is smart and say some jobs are already done. And so it will do only those which were not already done. And so this, for the convergency tests, can be quite a useful feature. Now this should be much faster because we have just 2 degauss values to calculate over these different types of K mesh and different types of smearing. So I'm at K point, K mesh 16 by 16 by 16, which means it should be over soon. And now, of course, I really used very, very large smearing. This was just, let's say, as an example. This 0.2 Rydberg of smearing, this is quite a high value. Okay, so this is Gaussian. You see, it even goes outside with this such a large smearing. It goes outside the range. Now this would be Marzari-Vanderbilt. So you can see it is flat up to a given point, and then it starts, the energy starts deviating from. And then if we go to Marzari, so this was Marzari-Vanderbilt, and now we go to Metfesdal-Paxton. We can see that in fact it is more or less for this denser K mesh, it's flat up to 0.2 Rydberg. So, but this is really going too far. And so what would be the message? The message would be that one can use, for example, for aluminum, some smart smearing like Marzari-Vanderbilt or Metfesdal-Paxton, with a smearing parameter, let's say something in the range of 0.01 to, I don't know, 0.05 Rydbergs. You can see here it is quite flat, and maybe this 8 by 8 by 8, you can see how it goes towards denser K, the result of the denser K mesh. And maybe for aluminum, I don't know, 8 by 8 by 8 K mesh is, it depends on the economy. If you want a faster calculation, you can use it. But if you want a very good calculation, you would use something like 12 by 12 by 12 K mesh. Okay. So with this, we have finished this example. So we can say that we can use, I don't know, 12 by 12 by 12, or if we want to make it calculation a bit faster, maybe 8 by 8 by 8, and smearing something like, I don't know, 0.02 or 0.03 or 0.01. And now we can go to the next example. And now this next example is not about convergency test. It is about post-processing. It is about how to plot charge density. So this CH dense, this is CH dense stands for charge density. Okay, and now let me just shift back to slides. So here you see these results that we just saw for the aluminum. And then here is the description how to plot the charge density. And the scheme to plot the charge density in quantum espresso is first make an SEF pw.x calculation, and then with the post-processing code pp.x, we calculate the charge density. And then Of course, this charge density is written to a given file, and we can use some visualizer like EXCRISDEN to plot the charge density. Now, this you see for the charge density, we have in the pp.x some parameter which is called plot num, and this is equal to 0, means charge density. And this plot num can go, I don't know, from 1 to about 20. So it's a code. And maybe this code is sometimes difficult to remember. So what is plot num 12? I have no idea what is plot num 12. But suppose that I want to plot a given property. And here it is this graphical user interface that is very, very useful. So PW GUI. So I open it. So this is usually how I do. Then I open a blank pp.x input file. And here you see I have this plot num. And suppose yesterday we did psi square. So I click psi square. And then I can go here to view, input file. And you see that for psi square, the plot number is 7. So this is, when I do post-processing, I always do like that because I never remember what this plot number codes. The other possibility is to go. The other possibility is to go to description, and then I go to plot num, and here I have the description of the plot num. So this is the other possibility. And then, of course, okay, with this, now we will do charge density. So I click on the charge density, but then I need to specify the plot. And so here are some data. So dimensionality of the plot, I say 3D, format of the output. And here I would say EXCRISDEN XFO format, whole unit cell, because this is super fast. If you do 3D with this, this is a slow option because here, basically fast Fourier transform for calculating the density will not be used, and this will be super slow. This here, basically, in this fast option, PP just dumps the density, which is already pre-calculated. And now I can look how the input file looks like. So you see, I have plot number equals 0, and then I have the plot name list. And I have one file, so the weight is 1, eflag 3. So this eflag, this is dimensionality of the plot, and then format of the output 5 means X of fast format, because this will be really calculated quite rapidly with this. Now let us look. Now I have too many windows. It's a bit difficult because I can just share one screen at a time. And here we have two examples. One will be charge density plotted with the use of pseudopotential, and the other with the potential. So it's a nice exercise. You will notice the difference. Okay, so here we will need to insert some values. And then here you can see that this is the input for the PP. And if I look here, eflag 3, output format 5, output format 5, and then the file out is where to plot the charge density. So it will be plotted in the file chdens.xsf. And then the script will also execute EXCRISDEN. With the same trick as yesterday with these orbitals, with these orbital densities. So there is a kind of a state script prepared. So EXCRISDEN will immediately open and make a nice picture. Okay, so here the comment says, please insert smearing the Gaussian K points. So smearing, I don't know, Marzari Vanderbilt. The Gauss 0.2. That should be okay. K points. Now I think I can afford 12 by 12 by 12. This will be fast anyway. And now I run this script. So now it's doing SAF calculation. Now it's doing post-processing calculation. So just to the scheme again. First, we do SAF calculation in order to calculate to have a self-consistent field solution. and then the PWX dumps files to the out dir where there is charge density, wave function, and so on and so forth. And then with PP, we read these files, and in PP we instructed the code, okay, I want charge density, and I want charge density to be plotted in 3D with X-Kristen format. And okay, this is now the charge density of aluminum. And you will notice that there is no charge because black means no charge. The brighter the color means the more the electrons are there. And you will notice there is no electrons around nuclei. And this is due to the use of pseudopotential. So we will remember the talk of Ralph Gebauer yesterday about these pseudo wave functions. And so the answer why this is so is there in this talk. And so for those of you maybe who are puzzled can go back and they will realize why this is so. And okay, so this was just here what we see is a plane expanded on what is it, 4x4 unit cell of aluminum. So maybe just to really give you the impression that this is a crystal, but now we are looking at the primitive, right? Because the code calculates the primitive. This does not give the impression that this is FCC, right? Because the code calculates the charge density in the primitive cell, which has just one atom in the cell, and this primitive cell of the FCC is 4 times smaller than this conventional, very nicely, let's say, tessellated unit cell. Okay. Now, if we go back to slides, you will notice here, and then the example, there is another example. So I now run this one CH dense. There is also example 2 CH dense, or no, how is it called? 2 CH dense PO. And here we will use PO potential. And one warning. When we will plot with this example, we plot basically what we plot, then you will find out this by yourself. We plot all electron valence charge density. So let's see what the number is this. This is 17. And here I can see 17. Maybe I should open it in MaX. So the first is all electron valence. You see plot number 17. And then we will also do all electron charge density. So valence plus core. This is possible with the PO. And what number is this? This is number 21. So if we go down, you see here plot number 21. And but there is, so when we use these features, we should use a very large cutoff energy for the charge density. Because if you look here at the charge density, you can see these oscillations near the nucleus. So remember the plot of Ralph Gebauer yesterday. So there are these wiggles near the nucleus. And to describe this with the plane waves, we really need a huge number of them. And this would be the all electron total charge density. And now we really see that because the aluminum, so let us open the periodic table. Aluminum has 10 core electrons, right? And so these are located around the nuclei. And so because in order to describe this, we need a large cutoff. So here it is a 500 Rydberg, but typically when I use these features and when I want to calculate the Bader charges, for example, from this all electron charge density difference, I typically use 1000 Rydberg or so. Here the example uses 500 Rydbergs in order to be a bit faster. But this is something that needs to be tested if you want to calculate the Bader charge, for example, where you need this PO potential and all electron charge density. You need to test what cutoff should you use for the charge density in order to obtain the converged Bader charges, for example. Okay, and then later on, you will also run this example and you will obtain a picture something like this and something like that. Okay, now we go to the last example of the day, and this is iron. This is iron, bulk iron, and if you look at the periodic table, we see iron has 3D states, and you will remember the talk of Ralph Gebauer yesterday. 3D is nodeless, which means that if we would use norm conserving pseudopotential, it would be quite hard. And Ralph has very nicely explained yesterday this, let's say, smart idea of the ultrasoft pseudopotential. And for iron, of course, we will use ultrasoft pseudopotential. Now, iron is not an FCC, but it is a BCC structure. And a BCC structure has E-brow equal 3. Again, so what are these numeric code for the E-brow? So we go to the Firefox, to the pw.x explanation. In the system name is E-brow, and you can here see all these codes for the E-brow. 0 is a free lattice, 1 is primitive cubic, 2 is FCC cubic, 3 is BCC, and so on and so forth. It's quite a number of lattices here. Okay, and then what we will notice, not only that we will now use ultrasoft pseudopotential for iron, but iron is magnetic. Everybody knows iron is magnetic. And because it is magnetic, we will notice a new variables in the input file, and these are n spin equal to, which is calling for, which is, let's say, turning on spin polarization. And then we need to set starting magnetization. We need to give to the code some input guess. If we would say starting magnetization is 0, we would end up with a non-magnetic solution. Okay, let me go back. So I will close this. So we are now example 3, iron. And now there are 2 input files here inside, iron AFM, and obviously AFM is not atomic force microscopy, but it means anti-ferromagnetic, right? And FM means ferromagnetic. Okay, so here, okay, first, iron is metal. So we have this occupation, right? Then it is magnetic, so n spin equal 2, and we give some initial guess for iron, 0.6. This starting magnetization is from 0 to 1 or from -1 to 1 if we have anti-ferromagnetic. And then, as Ralph Gebauer yesterday explained, if you see this US in the name of the pseudopotential, then it is an ultrasound pseudopotential. Okay. And so these are these new variables of today, and for this particular example, these 2 variables. Now, of course, this magnetic business will be handled in more details next week. But nevertheless, let me just show you how you do anti-ferromagnetic setup. And so I will open another input file. And it is very similar, but there are important differences. Because now in BCC, in the EBRAF 3 is BCC, is just 1 atom per unit cell. And because it's 1 atom per unit cell, we cannot have 2 different atoms, right? So we can just, with 1 atom per unit cell, we can just have ferromagnetic. So if we want to do anti-ferromagnetic, what we need to do, we need to do in a sense a supercell which is twice bigger. We need at least 2 atoms in the cell, right? At least 2 atoms in the cell, and then we can say, okay, one is let's say spin up and the other is spin down, or one is spin red, the other is spin blue, whatever you named it, they have to be different. And so for this reason, what we will do, we will take a primitive cubic. This is E-brow equal 1. And then there will be 2 atoms in the unit cell, and they will be labeled differently. You see with the same pseudopotential, but we label it iron 1 and iron 2. And then we have 2 atoms in the let's say in the cell, iron 1 and iron 2. And then we say, okay, starting magnetization of iron 1 is 0.6, and starting magnetization of iron 2, so the second iron, is minus 0.6. And with this, we have set up the antiferromagnetic structure in a sense. Okay. But for today, okay, you can do later on the exercise by yourself, but now I will just run the ferromagnetic iron. Okay, and so here, okay, let us just run this calculation. So let me just for once open the README file during the exercise. Okay, so I can run the calculation. Oops, didn't work. Okay, I do it. I do it like that. And this is what now I'm doing is another trick. For those of you, many of you know this. So this I pipe to T, and T will print to the file and to the standard output. And so here, if we look at the output file, you can see that the code prints total magnetization and absolute magnetization. So we see 2 point something per magneton per cell, which I think is not far from the experimental value, because we are now having the magnetic system. Okay, now I think is a time we move on and we go. Okay, here you will see the explanation for the antiferromagnetic. I will not do this example, but now we go to the convergence test for the ultrasoft pseudopotential. You remember Paolo explained this morning, when you have ultrasoft pseudopotential for the charge density, you will have two terms. So you will have this, let's say, smooth charge density plus augmentation terms. Augmentation terms are much harder and requires a larger cutoff for the charge density cutoff. And so here, so what we will do, we will scan different combinations of the wave function cutoff and of the charge density cutoff. So these are these two, E-cut wave function and E-cut rho. And so we go with dual. Dual is for historic reasons, because in the past, in the very, let's say, initial versions, it was E-cut wave function and dual. And the definition of dual, you can see here, it is just the wave function cutoff multiplied by dual, and this would be then the cutoff for the charge density. In the past, so it was a wave function cutoff and dual, and so this is the reason I use here the name dual. And so you see one feature of the Pwtk, you can write mathematical expressions. And so we will loop over a dual, and we will loop over a wave function cutoff. So let me go to example. So this would be example 1. So obviously it's just one script. So I open it. It should be the right one because it's the only one. Okay. So here you see, more or less the same as before, but maybe a bit longer because we are also collecting the results. So dual from 4, 8, 12. 4 would be default, right? Because if you do not specify the cutoff for the density, it is taken 4 times that of the wave function, right? So this is here. And 8 and 12 is, of course, a higher number. And then we will scan the wave function cutoff from 25 with a step of 5 down to or up to 50 ripples. Okay, so this is the script. Let us run it. Now it is running a bit slower because this Zoom is taking apparently a sufficient amount of of CPU, because when I tested without zoom, it was much faster. Now we are in cutoff 45 dual 4, so it will take a while. So maybe I should not wait. I think I also have the result in the slides, and the result is here. So you see here the result, and you can see for dual equal 4, this is the result. And then for dual equal 8 and 12, basically the two curves coincide. And so what does this tell you? This tells you the following. If I want to use, for the ultrasound, for this particular case, of course, if I want to use dual of 4, then I need to go up with the wave function cutoff to, let's say, 40 Rydbergs, because here the two curves starts to coincide, right? But if I use larger cutoff for the density, like 8 times or 12 times, then maybe I can go down all the way down to 25 Rydbergs. And I can use 25 Rydbergs for the wave function, and then let's say 8 times that, which would be, I think, 200 Rydbergs for 200 Rydbergs for the charge density. And okay, what is the advantage? The advantage is that in the code itself there is a lot of operation with the wave function, a lot of FFTs with the wave function, and much less FFTs for the charge densities. So we are doing a lot of business for the wave function and much less business for the density, which means that if I am able to go down with the cutoff, okay, here now I have the result. If I am able to go down with the cutoff for the wave function, the calculation will run faster. So this is the benefit. So use dual or use cutoff for the charge density, which is 8 times or 10 times that. You see for this particular example, 8 times is okay. 8 times that for the wave function, and you can go down with the wave function cutoff substantially. So here you can see that these 8 and 12 are coinciding. Okay. Okay, so this was about this, let's say, business of wave function versus density cutoff when we use ultrasoft pseudopotential. And now we can do, let's say, some example or some analysis, some post-processing for the iron, and this will be, so we will plot the density of states and the density of states projected to atomic orbitals, so that we will see some electronic structure of iron. And we will see how this magnetic solution looks like. So we go to this example 2, DOS. And okay, you can see the IDME file. And obviously there is just one script, which is dos.pwtk. So I open it. And here it says, please insert ECAT of wave function and ECAT raw values as determined in the ECAT exercise. Okay, let us do it. So I don't know, we could, let us take 13 Rydbergs. And then, of course, we saw that for the cutoff, we need 8 times that, right? So I just do as a mathematical expression. Be careful, when you do as a mathematical expression, you should not write like that. So it should be together, or else the Pwtk will not know how to interpret that. So this works together. This will fail. Okay. And okay, let us just what this example is doing. So we load input file for the ferromagnetic iron, which we have in the parent directory. Then we set the proper wave function cutoff and cutoff for the density. We run pw.x calculation, and then we do NSF calculation with a denser mesh, because here, if I look back, let us see what was in this file. it was 8 by 8 by 8. Here I just do a slightly denser mesh to have a better dose. I'm using tetrahedral occupations. This is a kind of occupation which is was not covered today. It is basically taking the K points and then it is making kind of not a cubes but a tetrahedra, and then it is interpolating. So if you plot a mesh, three-dimensional mesh, then you can do, let's say, a little cubes, right, from one to the next, and then each such cube can be subdivided into 6 tetrahedra, and then with these occupations tetrahedra, basically we are interpolating between 2 K points. This tetrahedra sometimes is nice for density of states. And then, okay, so we are running this NSF calculation. Then we are running the DOS calculation. So, okay, maybe this is a new code. You never, you didn't see it before. It's super simple. We can go here. We click DOS. So we see it has one name list, DOS, and here are some variables. It is the prefix and naudir. By this prefix and naudir, this pops up more or less everywhere, because this prefix and naudir tells to the program where are these files that pw.x calculated, right? When it did this self-consistent field calculation. And so this prefix and naudir will be here for these 2 weeks. So more or less every code. Not all, but majority of them. Okay, and then we do this DOS calculation, and then there is another code which is this wave function, projected wave function. This means you also have it here. This is a similar than DOS code. So DOS, obviously, from the name, it calculates density of states, and then you can plot the density of states. This projected wave function also calculates the density of states, but it calculates density of states projected to atomic orbitals, in this particular case to loading orbitals. And then you will see later on we can have this DOS projected to the iron D states, DOS projected to the iron S states, and so on. Okay, so at the end it is also running this, and then it is executing a new plot script, and we will see the density of states of iron. Okay, so let us run this example. Now it's doing SEF. Now it's doing NSEF with a denser K-mesh. Now it's calculating the density of states, and it will write to our files. Now it is calculating projected density of states, and now here is the result. This was the result of the DOS calculation. So let me try to zoom. So what we see, a majority spin, and this is typically usually how one plot these, let's say, spin polarized cases. Let's say spin up or majority spin is plotted like positive, and then minority spin or spin down is plotted as negative, and then you can see the two together, right? And so you can really see that this is a majority spin. Later, we will also see what is the Fermi energy, and it will be here somewhere. I hope you see my mouse. And so this would be vacant states, and you can really see that with minority spin, we have more vacant states than with majority spin. This just means that in majority spin, more states are occupied than in minority spin. Okay. Now, whoops, I press enter, and now I get density of states projected to, let's say, atomic S and atomic D states. And this is typical. Iron is transition metal. More or less, the electronic structure of transition metal, that it is similar in a sense. Well, if you look from far, it's similar for all of them. So we have a very flat S band that spans, I don't know, 10, 15, 20 EV. So here it goes from, I don't know, this is 5 down to 20. It depends how many states we calculate. And so you see SS is this, right? and this. And so in the S state, we have 2 electrons, right, per atom. S has 2 electrons per atom. And so we have these 2 electrons in the range of 20 electron volts, which is why the dose is so why this band or why the dose is very low. So these are very flat right here. On the other hand, in the D state, we have 10 electrons, and it spans, I don't know, from here to here, this is roughly 4 electron volts. So with the D state, we have 10 electrons in the range of 4 electron volts, and then it is obvious that the density of states will be quite high. And this is precisely what we are looking at. And typically, transition metal, bulk transition metals have one electron in the S band, because the Fermi energy would be somewhere here. We will do later on the exercise, where is the Fermi energy? Somewhere here, which means that roughly half of the band is occupied and half of the S band is empty. Okay, now to complete the exercise, so here we did not see where the Fermi energy is, right? And now, okay, so how to figure out the Fermi energy? Well, suppose that I'm new with the quantum espresso. I don't know how to do it because now everything is prepared. I can look at the README file, and there will be a recipe how to get the Fermi energy. So one way is that we grab this NSEF file. This is one way. And here I say, I got the Fermi energy is 12.8541 electron volts. Other way would be to look at the output file. And maybe this, I think, was explained today with Paolo. So we can look, because now we are dealing with the metal. So we have number of atoms in the cell, 1. Number of atomic types, 1, because it's just iron, right? Number of electrons, it is 8. So how many Consham states do I need for 8 electrons? Obviously 4. Why the code is taking the number of Consham states equal 8? Because it is a metal and we specified occupation. Or we specified explicitly the number of bands. So this is also possible. And I think this was covered yesterday by Pietro De Lugas. So you can say number of states is that high. But even for metals, as soon as you occupied smearing, the code will take some percentage larger number of states than are, let's say, the minimum needed. Then I can go down, and I can, so I'm trying to find, where is it? Where is it? Okay, it is printed here. The Fermi energy is, so this the output is NSF calculation is a bit different than for the SEF calculation. Another way to find the Fermi energy, I think, was also explained yesterday by Pietro De Lugas, is to look at the DOS file, and you have it here. You have it here. Now we can edit the GNU plot file. So all the GNU plot files have the GP extension. All the Pwtk scripts has the Pwtk extension. All the inputs has a .in extension. All the shell script has .sh extension. So this is good to know, because by extension you can recognize what file it is. And so here you see the instruction set Fermi energy to correct value. Okay, so here I have it. Or if I lost it by now, I look at this DOS file. It's here. I put it here. And then I can replot. And now we can see this vertical line. This is the Fermi energy, and this is more or less where I showed before you with the mouse. And this would be now this density of states projected to atomic S and D states. So this basically is density of states projected to S states and density of states projected to D states. And now you can really see that this is vacant. This is not occupied because we have the states occupied only up to Fermi Energy. And with this, you can immediately figure out that this is really the minority spin and this is the majority spin. So I think with this, we have more or less completed the hands-on for today. So here you also have an explanation of the scheme, how to do this dose and Pwtk wave function calculation. So you need to do, but I already described to you this SEF calculation. With non-SEF, we have a denser K-mesh, then we do dose, projected wave function calculation, and so on and so forth. So with this, I think I am finished, and if there are some questions, I can answer them. And otherwise, I wish you productive afternoon so that you will be able to do those exercises for those of you who did not follow me, who have just listened to me. But I believe that some of you have followed me and have already completed some of those exercises. So thank you very much for your attention.
Thank you very much, Tone. Yes, there are many questions on Slack which have been answered by other tutors and other speakers, and we have a few questions here in the chat. Do you want me to read them or you do yourself?
No, please read.
So, okay, yeah, these are from the streaming, the YouTube streaming channel. So the first one is for lattice parameter convergence should not will allow. Oh, no, okay, this is sorry. This question has been already answered by Paolo here and in the Slack, so we can go ahead. Shall we do K-point convergence, ECAT convergence before or after BC relax, starting from the experimental structure? So the previous question was whether to perform the difference between relax and VC relax. And Paolo answered, relax does not change the cell volume, VC relax does. It's an alternative procedure. For simple materials, the equation of state is simple and effective. And then the following question is, should we do the K-point convergence, ECAT convergence, before or after BC relax, starting from the experimental structure?
So I think that in this particular case, I think that the answer is relatively simple. So even if you take, so for example, we treated silicon and we treated iron, and we treated aluminum. So as far as K-point are concerned, if you take a experimental lattice parameter and you do a K-point test, I think that will do. That will do. Of course, the true lattice parameter will be a bit different, but I don't think this will change. This will affect the K-point convergence. So as far as the cutoff is concerned, it really does not depend on the structure because it's more atomic property. So the cutoff for the wave function depends on which pseudopotentials you take. So now for iron, we took ultrasoft pseudopotential. If we would take a norm conserving, the cutoff would be much higher. And this cutoff is atomic, so it depends on the pseudopotential, and the lattice parameter doesn't really have a role here. So I think that for both, of course, maybe with these K points, we need to have some provision. If I compress the structure, and for example, the structure becomes metallic, then yes, then of course, this K-point convergence can be significantly affected because we can go from non-metal to metal. But these are, let's say, special cases. Normally, I would say that this K-point convergence does not, let's say, critically depend on the lattice parameter, and taking experimental lattice parameter would be just fine. This would be my answer to this.
Okay. And is it convenient? Is it convenient to do the convergence of ECAT rho?
We've done that. We've done that. This was this dual. So, and the answer is here. So dual. So dual is, let me open a window because you can still see so we have E cut wave function, right? This is for the wave function, right? And then we have E cut rho. E cut rho. This is for the charge density, right? But here in this example, what we had, so here is a E cut wave function for different duals. And so as I explained, E cut rho equal E cut wave function times dual. So basically what we are looking at this plot is, we could also plot this in 2 dimensions if we would, in kind of plot in basically projection of the 3-dimensional surface projected to 2 dimension. So basically what we are looking at this plot here is wave function cutoff, and then each curve here means a different, in a sense, a different E cut rho, right? Because, okay, but it's case. So for example, for dual equal 4, this would mean 100 Rydberg for E cut rho. Here it would mean 120 Rydberg for E cut rho, and of course 30 Rydberg for E cut wave function, and so on and so forth. This point here, so let me, now I need to, okay, suppose that this is a 12 curve, right? So this point here, the cutoff rho is 12 times 25. This point here is 12 times 30. So in a sense, with doing this, we have run both E cut rho and E cut wave function test, and we have determined that, let's say, with dual 8, we can use E cut wave function of 25. And so at 25 with dual 8, this means that E cut rho would be 200, right? So this we did in a sense.
Thank you. Another question from streaming. Thanks, well understood. I agree. Maybe it is. Okay, this was still related to the VC relax. And I think, okay, here another one from streaming. For systems with more than 100 atoms, can you do VC relax at gamma point?
Okay. I think so. If you remember the talk of Ralph Gebauer yesterday, he plotted these, I think at a given point, these K points, right? Is a Brillouin zone. And now, the larger the unit cell, right? The larger the lattice parameters of the unit cell, the smaller are the reciprocal lattice vectors. The smaller are the reciprocal lattice vector, the smaller is the Brillouin zone, the less K points you need. Now, if you go back to the talk of Ralph Gebauer, where he plotted these K points, and now imagine that you shrink the Brillouin zone, which means that less and less and less and less key points are there. And this implies, yes, for a very big supercell, you can take a gamma point. So a single K point, if your supercell is super big, single K point is sufficient, so you can take gamma point. But of course, so what would be again, this is something that needs to be tested. And suppose that we have for a cubic unit cell, this is super simple. Suppose that my lattice parameter is A, right? And for this A lattice parameter, we saw that we needed, let's say, for aluminum 12 K points, right? Now, suppose that I do a supercell and I do a 2A by 2A by 2A supercell. Now, because my supercell is twice bigger, this means that the Brillouin zone will be twice smaller per direction. So I can take 12 divided by 2 for the 2 by 2 by 2. So I can take 6 by 6 by 6. Now I imagine I go to 3 by 3 by 3 supercell. A 3 times larger cell means a 3 times smaller Brillouin zone per direction. So I can go to 12 divided by 3. So 4 by 4 by 4. would be fine, right? Then I go to 4 by 4 by 4 supercell, which means 12 by 4. So 3 by 3 by 3 K points would be okay. And now you see, this is the reason why I like 12 by 12 by 12 K mesh so much, because it has a lot of these divisors. So you can divide by 2, you can divide by 3, you can divide by 4, you can divide by 6, which means that if you go from a unit cell to a 2 by 2 by 2 supercell, to a 4 by 4, to a 6 by 6, you can figure out what would be the equivalent K meshes. So for 6A supercell, 2 K points would be enough. But if I do 12A supercell, then at this point, because I saw that, for example, aluminum 12 by 12 by 12 K mesh is enough. If my supercell is 12 by 12 by 12, this implies that I can easily take a single K point and I will be at the same precision as for the unit cell that, when I use 12 by 12 by 12 K mesh.
Thank you. Another question, of course, for participants, since now Tone has finished the explanation, you can write here on Zoom if you want some questions to be explained on voice by Tone, or otherwise you write on Slack in the way you are doing so far. So here, another question here, for which total energy difference should I consider the calculation as converged? Is there a rule of thumb or some safe value that I can be satisfied with?
Okay, this is in a sense a tough question which does not have a single answer. Let's say that as a rule of thumb, if you converge to a milli Rydberg per atom, this should be more or less okay. But this should be tested, in principle, this should be tested for every property that you're interested in. It depends on the context, right? It depends on the context. Now I wanted to say something more here. I had in my, but now I forgot what I wanted to say. It's another issue, but I just forgot. It's another issue. Ivan, can you repeat the question? Maybe
Sure. For which total energy difference should I consider the calculation as converged? Is there a rule of thumb or some safe value that I can be satisfied with?
Mm-hmm. Yeah, so as I said, it depends on the context. So maybe 1 millirad per atom, but then you can test for every property you're interested in. But so even, I'm sorry, because I wanted to tell something more, but now I forgot what. So I cannot remember. I'm sorry.
Yeah, sure.
Even the question didn't help. If I will remember, then I will write on the Slack.
Okay, no problem. The question is also posted on Slack on day 2, channel May 18.
There is something more I wanted to tell, but I'm really sorry I forgot while I was speaking.
Yeah, sure. We have Slack and many other occasions. So yeah, no problem.
Yeah.
Now I remember. So suppose that you have a semi-core states that you treat semi-core states explicitly. Then these are very hard usually. And if you would want to converge the energy to within a millirydberg per atom, then this would require a super high cutoff, right? In such cases, maybe you can do another test. So you're interested, I don't know, in the structure, or you're interested in the cell volume. You can, instead of doing a convergence test with respect to the total energy for such a pseudopotential with the semi-core states treated explicitly, you can do a convergence test with respect to, I don't know, lattice parameter, with respect to forces, with respect to the property you are interested in.
Thank you. So another one, thanks here for this great presentation. Can we optimize the atomic position and keep unit cell? I guess, yeah. Yeah,
this is a question that is answered, that will be answered tomorrow. Tomorrow, in the morning, you will have a lecture about relaxation, about variable cell relaxation, about NEP, and then in the afternoon, in the hands-on session, Ari will present the relaxation, variable cellular relaxations, and also NEP calculation. And now I think here the answer depends. If you are calculating, let's say like we did today, silicon or aluminum or iron, which are cubic structures, right? So we can just scan. We can do a scan over the lattice parameter, and this is quite efficient, and is usually okay. Now, if you have a unit cell which is not cubic, which is triclinic, for example, which has A, B, C, alpha, beta, gamma, then of course you have 6 parameters to optimize, and then I think in this case I would highly opt for variable cellular relaxation.
Thanks again. So another here, thank you for the beautiful presentation. What is the criteria for categorizing magnetic materials as ferromagnetic or antiferromagnetic with respect to the total magnetization, absolute magnetization, and magnetic moment?
Okay, so I think that a majority of this will be handled next week because there is a magnetism day. So, but if we just stick to this iron example, right? So if all the magnetic moments are pointing, let's say, in one direction, then this would be ferromagnetic. With the antiferromagnetic, we have kind of, let's say, one pointing up. One atom, the magnetic moment was pointing up. For the next atom, magnetic moment was pointing down. And then, of course, then if you do the sum, you would get 0. So antiferromagnetic, the net magnetic moment of antiferromagnetic material is 0. If you consider this antiferromagnetic iron, one atom up, the other atom down, right? And so I think that for today, this should be more or less enough explanation, because more will be next week. Maybe just the difference between total and absolute magnetization. So the total magnetization, I think, is you do the sum. You do the sum, and for antiferromagnetic it is 0. And absolute is you take the absolute values of each moment, and that means even for antiferromagnetic, if you take the absolute values, right, plus minus, there would be just absolute, and it would have the code would print this absolute magnetic moment would not be 0, but total magnetic moment would be 0.
Okay, so another question from the streaming now. How can I include the electric field effects in the input file?
The electric field effects, okay, these I don't know whether these will even be covered. So I think it is better that I show here. There are some variables like this deep field and this TEF field, and so there is a series of variables. So I suppose that this, so you want to put, suppose you have a surface and you want to put your surface in a magnetic field, and then, or you want to do a dipole correction. It is a similar thing. It is related to this deep field, but there is a series of variables that you need to let's say plug in order to have this electric field or this dipole correction activated. And so maybe I will write answer later on Slack how you can do that. Okay. Because it's something that even I need to look, because there are 5 or so variables, 3 variables that I don't know by heart. I need to look at it. So I will post the answer to
yes.
Slack.
So here we have, I don't see any other question from the streaming. Yes, the last one was this one about the electric field effects. Here on the chat, I see this question. Can you please repeat how did you extract the plot from prog from PW guy? But yeah. I think that if Mal, you post this on Slack, you could receive more direct assistance, or I don't know, Tone, what do you think? Because
but for this PW GUI, I can show this is trivial. So I can do again. So if somebody didn't catch this, maybe it will.
Okay, please go ahead.
So you open it, and now suppose, so the question was referred to this plot number, right? And plot number, so you pick the right, okay. So this means new here, right? Create new, or you go here. New PP input. Okay, and now here you see this plot number, right? And suppose I want psi square, I click psi square, and then I go to view, input file, and I have it here. And typically this is how I use it. Then I just copy with mouse to my input file. So I copy this and I put into my input file. Another useful feature, because this PW GUI is a kind of input builder, right? Another useful feature, maybe for the beginners, is for the pw.x. Now, of course, here in pw.x, there are hundreds of variables, and this is confusing. Maybe you cannot find. Maybe this, for the PW, this is better. Here you can search and you can find, right? But there is one feature here which is very, very useful, And this is the following. Here you see I have a type of calculation. If I click self-consistent field, and then I go to view, input file, I see the structure of the input file for SEF calculation. So this tells me, okay, I need a control name list. I need a system name list. I need electrons name list. I need atomic species, atomic positions, and I need a key points. So these are the fields that I need. Now let us go to relax, ionic relaxation. And maybe just one explanation here, because I noticed that students who are new, they are many times confused with what is this ionic relaxation. Do we want to do sodium cation and chloride anion? And the answer is no. Ion, also we have the name list ions. This is a pseudopotential jargon, because in a pseudopotential, we do not have true atoms. We have pseudo atoms because we are treating nucleus plus these core states implicitly, and this then can be seen as an ion. So basically in a pseudopotential jargon, ion would mean atom or nucleus, right? Because I know that students are sometimes confused with this word ion. Now, this ionic relaxation then means that I want to relax the structure of, or if you want, this is a relaxation of a molecule, a relaxation of coordinates within the unit cell, or so on. And now, so I ticket this relax calculation, and now I see the structure of the input file. Now you see, before for SEF calculation, there was no ions name list. Now I ticket relax, and I have the ions name list, right? Now, if I do VC relax, this will be tomorrow, you will notice that not only I have ions name list, but I also need cell name list. Now the name list can be empty, which means that default values will be used, but it needs to be there. Another thing, now let us go to here, system, and let me pick eBrow equals 0, which means free lattice. So free lattice means that I will specify the lattice parameters, the lattice vectors myself. Now in this case, I go to input file, okay, I see eBrow equals 0, and I have a cell parameters card. So here I will specify a lattice cell vectors, right? So by doing this, so maybe using for pw.x is confusing because it's too many variables, but at least at the beginning, if you use it, you can have the idea what is the structure of the input file for a given calculation on, let's say, for a given Breiweis lattice. And so suppose that I tick here cubic, and you see I just need to specify CLDM of 1. And there are two different ways how I can specify the lattice parameters for the predefined lattices. One is via cell DM, which means cell dimension, and then this is specified in Bohr units, or via A, B, C cosinus AB, cosinus AC, cosinus BC. So one or the other, you cannot mix. And so for cubic QC, I need to specify A. Now let us go to some, I don't know, triclinic or monoclinic. You see, for monoclinic, I need to specify A, B, C, and cosinus AB. And maybe for triclinic, the answer is clear. For triclinic, I need to specify all the 6 lattice parameters. So maybe for this, this graphical user interface is useful. Okay.
So thank you very much, Tone. I think we have answered all questions because we have no more questions from streaming. And of course, on Slack, I think that almost all questions have been answered. But of course, if they are not now, they will be in the next few minutes or hours. So for sure, everyone who posts on Slack will receive an answer. So no problem for that. And I don't see any other question here. Okay? Yes. So maybe it's time to close now. It's 12:30 almost. So if you have more questions, because maybe you will keep doing the exercises in the next minutes or hours. So if you have troubles, you still want to ask something, of course, as usual, post it on Slack and you will receive an answer. So we can keep using the Slack channel. Thank you very much, Tone. And here there is plenty of messages here. I didn't read them all, but there are plenty of messages with extremely clear presentation. Thank you so much. Amazing presentations here, very much. Thank you. So really, thank you, Tone, for this presentation. And we will meet again with the Tone and Pietro De Lugas tomorrow, 8:30 here on Zoom. So good afternoon or good evening or good morning, whatever, to everyone. And yeah, goodbye. See you tomorrow.
Okay.
Bye-bye.
Bye-bye. Bye-bye.
Bye.